All right, welcome back. Let's take a look at one of probably the most popular tests. And the reason why this test is very popular is because in most cases, you're not really just going to be restricted to two populations or two groups. Normally, there's a lot of different groups that one may be interested in. Here's some examples. And what I want to note is that you're usually interested in a quantitative variable. So let's go ahead and say that you're interested in the variable x, which is going to be, again, some quantitative variable. But that variable, you have reason to believe, may be different for different groups. So there's going to be some qualitative variable. So there's an overarching qualitative variable. And that qualitative variable has different values. So let's go ahead and take a look at our first example here that says the time spent studying last week according to year in college. So in that case, the random variable of interest x is, of course, the amount of time that students spent studying. Notice that that is quantitative. And what we want to point out is that that is then grouped according to this qualitative variable. Uh, um, and that qualitative variable is class standing. So that class standing would give you group one. So that's one level. Group two would be another. Group three, and so on until we get to senior. All right, so that's for that example. The next example we're looking at, for example, the weight loss. So if you're, in this case, now you're interested in the amount of, the number of pounds that people actually lose if they were to use different techniques. And so the techniques that we're interested in here are, for example, if somebody only focuses on nutrition, maybe somebody only focuses on exercise, somebody uses a weight loss drug, and then maybe we have combinations of the different strategies. So for example, nutrition and exercise and so forth. Here's another one, hours spent socializing according to personality type. So in this case, the personality type, however you may break those down by, would be the qualitative variable that produce the different quote unquote populations. All right, and same thing. So the last one we'll look at is, for example, salary 10 years after graduation. In this case, salary, how much somebody brings in every year, would be the qualitative variable. And of course, we're interested in comparing these three or more groups. And one of the central questions to this is, do we have the same mean according to these different groups? So if you have population one and you're interested in mean one, what is the mean for that first group? Then you do the same thing for group two, look at the mean, and finally, until you get to the last group. And the main thing that we're going to be interested in answering in this section is whether all of those means are the same. So we're usually going to write it like this. Is mu1, the population mean, the same as the population mean 2? All the way until we get to the population for group K, because we have K different groups. And that's going to be your null hypothesis. So we're going to assume that all of the means are the same, because why would, for example, the weight loss be different, right? Remember, the null hypothesis is the no change hypothesis. We're going to just assume, for the sake of argument, that the values are the same. The values do not change. So if I, for example, look at the cost of coffee, why would the cost of coffee be different if I go to Starbucks versus Coffee Bean versus Pete's Coffee versus Norton's Coffee or any other coffee chain for that matter, right? They're really, if it's the same product, we believe that it really should be the same. And that's the logic that we use here. Time spent studying, well, we really think that, students should be spending the same amount of time no matter what. In practice, though, this might be different. So my alternative hypothesis is whether I can actually detect a change. And if at least one of them is different, for example, if group 2 here is larger than all of the other ones, then that means that one group does not have the same average as the other. So the alternative hypothesis will be that at least one of the means is different than the others. And we're more or less going to stop here. We can actually do more. If you look at the notes, maybe further out, we can actually come up with an idea of which mean is potentially different. But if we can answer this question of, so do we have evidence to support the null hypothesis, or do we have evidence to support the alternative? Then we can go ahead and then investigate further. So let's go ahead and start with the main strategy. The main strategy that we're going to employ is called a one-way analysis of variance. Don't know why there's an S there. It's a one-way analysis of variance. Let's just get an intuitive idea of what the analysis of variance is all about. So let's go ahead and take a look at these different groups here. We have group 1, we have group 2, group 3, and group 4. And then here you have your variable of interest. And same thing over here, case number 2. So again, we have our variable of interest. We have group 1, group 2, group 3, and 4. And remember that these 4 groups are just simply one of these different qualitative variables. And the variable X could, for example, be the time spent studying. And let's go ahead and just try to understand what is going on here. So in group 1, so notice that I'm asking you, what are the differences between the two cases? Here's case 1, and then here's case 2. There are differences between these. And look at what we did here. We have X1 bar. This is the average. We have X2 bar. We have X3 bar, so that's the sample mean for that group, and we have X4 bar. And what I want to essentially do is I want to say, well, if I were to compare those averages, are they different? And the answer is no, because that average for my first group is here, average for that second group is here, average for the third group is here, and then average for the fourth group is right around the same thing. So the averages are more or less pretty central. And notice that the averages here are actually the same. So they have the same average. So it's very similar data. And here we have X3 bar, and then finally X4 bar. So the centers are the same, but there's a difference in the variability. So there's a reason why this is called one-way analysis of variance. What we're going to do is we're going to take a look at the variability. So how much does the data vary in the group? And let me just go ahead and give you guys an idea of that. So for example, in group 1, my data varies from here to here. So there's a lot of variability in that group. Notice that for group 2, same kind of variability. I'm only looking at the center 50% of data. This is the amount of variability in that group. And then look at the amount of variability in this group. And then here we have the variability in that group as well. And now notice that there's a lot of overlap. In the data across groups. In case 1. But if we look at case 2, look at the amount of variability we have here. There's this much variability. In group 2, there's this much variability. In group 3, there's this much variability. And then finally, in group 4, there's this much variability. And what I want to point out is that there is not a lot of overlap. What I mean by that is if you were to project this variability on the same axis, then this is the range over where we have our data for group 1. Then let's take a look at the range where we have our data for group 2. It's right here. So let's put that on the same number line, so that'll be around here. And notice that these are not even overlapping. So the variability in group 1 and the variability in group 2, you can see that there's a clear gap in the center 50% of data here. And that right there gives us evidence that, ooh, these might be different values for across different groups, because the data that was observed for group 2 varies across here in this interval, right? They're higher overall, whereas the values for group 1 are lower. So case number 2 actually provides stronger evidence for a difference of the random variable x that you're interested in across groups, for evidence, stronger evidence for difference of x, value x, across different groups. And again, that has to do because of the variability. Let's take a look at the variability for group 3, how that compares. And then we'll go ahead and take a look at the variability for group 4. So group 3 varies over this range. And if I were to project that on my number line, it goes over here. Something like that. That's group number 3. That's where the data range is at over. And then group 4 finally also has a range that's roughly over here. So again, let's project that as best as we can somewhere here. All right, and let me go ahead and just note the following. If I were to do a similar picture to what I see here, right, trying to visualize all of the data together instead of it being separated horizontally, then you can see that the pink, orange, and light blue actually overlap. So these data values right here, there's overlap. However, if I were to look at the center 50% for group 1 doesn't really overlap with any of the 3 groups. And that right there is what we were after. We were after, is one group different? Is one group very different from the rest? And what we're seeing here is, yeah, it looks like group 1 is more different, tends to be more different than groups 2, 3, and 4. So case number 2 shows that group 1 may be different. Because I overall have values that are lower. Remember, you're measuring the same thing. So think of, like, for example, study time. And this is study time by college level. So we can go, or year. So here, group 1 could be freshman, group 2 could be sophomore, group 3 is junior, and then group 4 is senior. And what this basically says is that my box plots show that freshmen tend to have lower study times overall because of this overlap, versus group 2, 3, and 4, they share a lot of values over a common range. So this is what we mean by analysis of variance. We're looking at how does the variability change when you look at the overall variability. So that's what I did here, the overall variability, versus when you look at the colors, the variability within a group. And notice that the variability within a group is very short. Like these are very short squiggles that I did, like the purple, the light blue, the pink, and the orange. That's what I mean by variability right there. And what we observe is that in general, we're going to basically go ahead and ask this question. Is there evidence that all of each of these groups came from the same distribution? So if these groups really are random groups, we're going to need to make sure that we have a random sample. We're going to go ahead and say, well, if I were to take a group, for example, group 4, is it likely that, and it's likely that I get data like this, group 3, again, this could be a random sample. But now check this out, group 1 and 2, they're much lower than group 3 and 4. And so if this was a true random sample, it would be unlikely that group 1 and 2 are much lower collectively than group 3 and 4. And so case number 2 demonstrates the what the analysis of variance is. Okay, so let's go ahead and let's get a little bit let's build the intuition a bit more over this by looking at the following. So let's skip page 14 for now. What we're going to go ahead and measure is the variability between different groups versus the variability within. So again, here are the keywords: between versus within. So if you have group one, for example, would follow some kind of distribution here under the gold, and they will provide an average, mean one. So that'll be group one average. And that was the center of my box plot right here. So the center right there is mean one, mean two, mean three, and mean four. And you don't have to actually memorize this, because we're going to use the computers to compute all of the means and standard deviations. So really, the whole purpose of this, the next 5 minutes or so, is just to build that intuition as to what exactly is the ANOVA procedure computing. All right, so you take group one, you compute the mean. Take group two, compute its mean. Take group three, compute its mean. And here I'm going to assume that we stop at 3. Then you're going to look at the overall mean. So what is the overall center of all of the data if you were to group it together? So I should have gotten rid of this page. Sorry about that. So again, we're going to compute the center 1, center 2, center 3, and until you are done with your number of groups. And then you're going to pretend that you're looking at the overall center. So pool all of the data together, and then just here, let's call it just X bar. And that's going to be called the grand mean. So that would be the true center if the data were not separated. And then what we're going to do is we're going to try to get an idea of how much variability is there between the groups. So from one group to the other, you can see that there is a lot of variability. Group 1 and group 2 are more or less fairly close to each other, but group 3 is far away. Group 3 is over here. So what I'm going to do is I'm basically going to say, well, how much does each group average differ from the overall mean? And that's what this is. So here, X bar L is the average for group, and I think that should be an I. Looks like an L. So that's the group mean. Group I center. And then we're subtracting that from X bar, which is the overall center. We're squaring it to make it positive. Remember, we did that a lot of times. And then we go ahead and scale that by the number of values that are in group 1. So I would take group 1 minus the center. That would be this distance right here. Group 1 minus the center, that's this distance. I square it to make it positive, and then I multiply by the number of observations in group 1. Then do the same thing for group 2. So you basically just continue adding this deviation from the group to the overall center. And then you go ahead and create what's called the sum of squares due to treatment. So that's the SST. So this here is these, think of like the variability between the groups. And what we do is we divide it by the number of groups to get what's more or less an average. So think of like a standard deviation, right? We divide it by a value. In this case, we're dividing by k minus 1. And we're going to get something called MST. So the mean square due to treatment. You don't have to worry too much about this, but just remember that this is the variability between different treatment groups. So that's this guy right here. And then we're going to go ahead and look at the variability within the groups themselves. So if you take a look at group 1, we already have group 1's average. That's X bar. I'm going to use a different color now, red. So you have group 1's average. And then I'm going to go ahead and just take a look at, for example, this could be X11. So that's value 1 in group 1. And then this could be X21. So second value in group 1, sorry, X31. And so a value here is just going to be denoted by XI1. So data value I in group 1. And then you would do the same thing and basically just find the standard deviation of that. So if we look at the formula, you can observe that XIC is basically a data point in group I, or maybe I should say group C because we're using that index. And then we're subtracting that by X bar C, so that's the mean in that group, mean of the group, and we're squaring it to make it positive. Go ahead and add that deviation for group 1, then do the same thing for class 2, and then finally class 3, and so on. So you basically get the standard deviate, the variance actually. So x1 squared is the variance in group 1, and you multiply that by n minus 1 minus 1. So that would be the degrees of freedom in that case. And you basically just add up all of the variances. So the variance in group 1, variance in group 2, variance in group 3. And what this tells you is how spread out every group is. So it's essentially measuring these values right here. So it's giving you an idea of that variability in the middle. Here I just sketched it out by going over the center 50%. To be more precise, you have to actually go through that formula. Okay, so here's this length, and that would be a measure of the variability in group 3. You do the same thing here, measure variability in group 4, so that length. So basically, what's the variance in group 2 and in group 1? And then you go ahead and you add it up in a weighted fashion. So if you have a lot of data points in group 4, that value is going to be more important for group 4. And you can see that here in case 1, a good measure of the average. So here, let me go ahead and just write it out. So sum of squares due to error, a good value without doing any computation, let me just get an average length, could be this length right here. And because it's the overall average, it's not going to be called SSE anymore, but rather a mean. So it's going to be an average. So the average variability within groups is this red distance. But if you look at the variability of the center to center, let me go ahead and write that in this green here. So here, the overall center should be somewhere around here. And if you look at the average distance of those means, then some length like this, for example, could be the length, could be the average of each of these lengths. So the MST, the mean squared due to treatment to the different groupings, is this little green guy. So the overall distance of the centers, those are these centers, overall gap here in the centers is roughly this green guy. So you can see that the groupings don't really have a big separation here when compared to the overall variability to the group. So if you compare the length in green to the length in red, there really is no significant separation across the different groups. So let's write that down. So for number 1, there's no significant difference across groups because the groups themselves have a lot of variability, right? It's that average variability in red dominates the data set when you compare that to the variability in green. And notice that for this second example, it would be a lot different. So for the second example, you would take the overall center. Overall center looks like it's about here. And then you would ask, how far away is the rest of the data points? So let me, again, do that in green. So in green, it would look about this value here. Then this to the overall mean could be maybe this value. This to the overall mean is, again, this value. And then the red one would be higher. So it looks like a value here for MST would be maybe a value like that. It'll be maybe that length. That green length there could be the average deviation across the different groups. And then in red, we can go ahead and show the deviation within the groups. And so we've already seen that. Here it is in red. And notice that it's a lot smaller. So the average, so the MSE, would be maybe something like this. And what I want you to do is I want you to compare. So here's your MST, here's your length. So there's the average length across the different groups. And then here's the average spread of those different groups. And notice how much closer this is. So the MST seems to be right around the MSE, which means that there is a gap in the groups. And what I want to point out is that if the further out these groups are, so here's the gap. So here's the overall center. Now look at how far away this center is. It's this much. Look at how far away this center is. It's this much here. This top one is this much, and then this top one is this one. And then you compare that length. So again, it would be like this purple length right there, getting compared to the red length, which would be the variability within each group. So it would be something like this. So if I compare that to this length, notice that they're pretty close. So the smaller MST is, like in case one, the less evidence you have that there is a difference by grouping this data. So let's go ahead and make this more precise. And so what we're going to look at is we're going to look at the ratio between this. You're going to look at the ratio of the variability between groups. So it would be the the green distance. So we're looking at how many times. So there's that green distance between the groups. And then we're going to look at the variability within the groups. And that's in red, like this. So remember what we said, if there really is no difference between these, then the variability between the different groups should be small. So let's write that down. So if the ratio, which is this MST over MSE, so if the ANOVA F stat, this is called the F statistic. So if the F statistic is really small, if it's really close to 0, it means that MST is much smaller than MSE. So the MST is the green one. And so remember, if we go back, the average length across groups, if that's very small versus the overall variability within the group, we have case one, which means that there's a lot of overlap. There really is no difference in the centers by looking at this at the different groups. And so it looks like there's no significant difference across the groups. Versus this case right here, notice that the ratio is a lot closer. The purple one versus the red one, they're almost close to 1. So you're going to see that if, for example, the variability for different groups was like this, if it was only this long, so if that's the overall variability within the group, and then this is the overall variability across the different groups, then you can see that this variability is much larger than the variability within the groups. So that means that in order for you to get the variability here, it means that the groups have they vary a lot. And that's kind of what we get here, that there's a lot of separation between the groups. So that's the way that I want you to think of the green one. Okay, the green one is the separation. Across the groups. And so if that separation across groups is much larger, then it means that there is a difference in the values across groups. And this is a positive value over a positive value. So if the bigger the F ratio is, so if F is much larger than 0, then that means that there is a separation across groups. So there is a difference in whatever random variable you're looking at across those different groups. This is more or less the output that we're going to get. So you don't really have to memorize this. You're just going to read this off of StatCrunch or off of your technology. And what we're interested in is we're interested in the F statistic and the p-value. The p-value is going to be the easiest way to do this. If you're going to use an F statistic, you have to use the F distribution. And so that's why this page is here. I should really change this. All right, so the F distribution is basically what happens when you look at variance over another variance. I don't want to bore you with the details because it's honestly not that important for us. You just got to know that when you're doing the ANOVA test, you're going to use an F distribution, which has 2 degrees of freedom. So for every different value of degrees of freedom, right, if you take sample after sample after sample, you're going to get a pattern. And so the pattern that we get is we end up with this highly skewed picture, kind of like a chi-squared picture. And again, every combination of degrees of freedom will give you a slightly different curve. So we have the curves here. So if the degrees of freedom is 1 and 1, you get the red curve. If it's 2 and 1, you get the black curve. And most of the time for us, we're going to get something that looks like the blue or the green curve. And the larger this is, the closer this goes to something that more or less looks normal, which we've seen before. So to just practice doing this, let's go ahead and find a critical value of alpha. Oh, and I should say this. You either have a small F ratio or a very large F ratio. So this will always be a right tilt test. So I'm only going to go ahead and find the right tilt. So let's go ahead and find the critical value of F if I have the following. If I have the numerator of 33, so N1, 33, sample size 1, sorry, is 33, and sample size 2 is 30, and then we look at the variability. So we're looking at S1 squared over N1 divided by S2 squared divided by N2. So if we go ahead and look at this, it's known that this has an F distribution. And remember that as soon as you know the name of the distribution, you're in business because you know everything there is to know about this distribution. So let's go ahead and sketch it. It's going to be a right tilt test, and it needs to look skewed right. So start at 0, 0, and we're just going to go up and then go down this way. And here's your number line, and then we want a right value here of area 0.05. So what they're asking me is, what is this F statistic? And so F sub alpha would be equal to something. I guess the technical name for this should be F sub alpha, where you have the degrees of freedom listed down. So it should be F sub alpha, and your degrees of freedom for the first number is N1 minus 1, because remember, you subtract a 1, and then the second sample size minus 1. So that's the technical way. I'm not going to write it like that anymore. Let's just go ahead and use stack crunch. So the degrees of freedom 1 is N1 minus 1, which is 32. And degrees of freedom 2 is the second sample size minus 2. And in that case, that's 29. So let me go ahead and throw that into StackCrunch. Remember that anytime you have this picture, you can find a value, for example, if you know the probability, or find the probability if you know the value that you're interested in. So let's go to StackCrunch. Remember that we go to Stats Calc whenever you have a picture like that, and you go to the distribution that you're dealing with. In my case, it's an F. Let's type these in here. So N1 was 32, and the second one is 29. So I get a picture that looks like this. 30, let's verify, 32, and 29. So just keep the order like that. Whichever one comes first, type that one in first. And I want an area of the right to be 0.05. And I want to confirm that the picture that I get here is very similar to the picture that I drew on my paper at the beginning. And so therefore I have my critical value right here, 1.84. So there it is. This says that if your F statistic is greater than 1.84, then that would be significant evidence against the null hypothesis. And so it makes a lot of sense because I'm saying as soon as the separation here, this green length, is right around more than double roughly the variability of the bottom one, then I'm going to go ahead and say, yeah, there's a pretty substantial difference in the grouping. And the actual value that we need is 1.84. All right, so that's fairly it. Let me go ahead and show that here real quick. So you have f sub alpha. Here it would be the reject the null hypothesis. So there is a difference across the different groups. And if you land here, that's the fail to reject the null hypothesis, which means that you would support the claim that the means should look like they're the same. All right, and that's the new procedure for checking whether the means are the same or not. For your work, make sure that you try this one. Okay, repeat the same work and complete B. So if your numerator and denominator sample size is of 20 and 46, can you go ahead and find the critical value if you were doing the F statistic approach to ANOVA? In the next video, we're actually going to run through a full-on hypothesis test. Remember that you only needed to know the basics of this, which for all intents and purposes are you need to understand when we use ANOVA, and that's for different groups, and know the null hypothesis, the alternative, as well as roughly what it is that we're looking for. It's fairly technical. I really wanted to skip all of this, but you can't really appreciate ANOVA unless you know that you're looking at the separation across the groups compared to the overall amount of separation within the group. So that's the variability within the group. So that's the green length versus the red length. When we do examples, I will always do a box plot check to make sure that everything looks very similar. If you reject the null, then that's case 2. If you fail to reject the null, that would look more like case 1. So we're always going to go ahead and use box plots to support our hypothesis test. All right, I'll see you in the next video with a full example. Take care.